Hello, everybody in the room, and hello, everyone online. I hope you can hear me okay. Thank you all for coming. This is the third Early Careers Group Manual of Geotechnical Engineering event. I will move on from this first slide. Just first things first, for those in the room, there is no scheduled fire alarm or anything tonight, so if you hear the noise, it's the real deal. So the fire exits are left and right of us. Follow the green arrows and we'll rendezvous outside the building, following the map that you can see on the screen here. So welcome tonight. This is session 3, groundwater considerations. So we will have 3 talks, small talks tonight, followed by a discussion group at the end, where we'll share some thoughts and questions and discuss the things that we've just heard. So with me tonight, we've got Mark Lee from Jacobs, William Powrie from the University of Southampton, and Martin Preene from Coffee Geotechnics. So we'll have 3 short presentations and then an open discussion at the end, where it'll be a really nice forum to sort of share thoughts, both for those online and in the group. So just a quick thank you to our series sponsors that are supporting us across these sessions, who are on the screen here. And really the aim of the Early Careers Group for these sessions is to provide updates on the 2nd volume of the Manual of Geotechnical Engineering to a wider audience, highlight that this resource exists and highlight some of the changes that have happened over time. And it's really important to do that so that we can identify any issues or opportunities for our industry in the future. And this is a really nice way, we thought, of engaging between early career individuals, which our group is focused on, but also those that are more experienced than us and in their mid to late careers as well. So this is part of the series. We're on number 3. There is still a lot more planned beyond us, covering key chapters of MOGE. You can see a few more on the screen that will be coming out in the upcoming months, each one hosted by a different early careers professional. And just a bit of a flag for the next one, ground investigations. It's back in London at Arup offices. Either scan the QR code now. Yes, you're already scanning the QR code, I like it. Or are you just taking a photo? Oh, you took a photo. Oh, okay, well, there we go. You could do that as well. Maybe come along. So that's upcoming on the 4th of June. So audience participation is the key of today. It's not just 3 lectures. We'd love to have some questions or feedback, any points that you want to raise throughout. We are going to be using Slido for question and answer tonight. So that's in person and online. For those of you that haven't used Slido before, very simple, go to sli.do. There's a code to type in, which is shown on every single slide, so there's no excuse not to use it. At any point tonight, raise a question, a thought, anything you want for any of the speakers or anything general. We'll probably come back to those at the end of the session, but we can be on hand for any immediate questions that we need to answer. Okay, so that's it from me now. So the first presentation tonight is from Mark Lee. It's our introduction and the relevance of groundwater.
Thank you very much. It's a very pleasant evening to be here. Sorry to drag you in from the sunshine outside, a rare sight these days. I am fortunate to know some of the people in the room. For some of those that I don't, a quick introduction to myself. I'm Mark Lee. I'm the holder of the world's longest job title, I think, the Head of Technology for Engineering Hydrogeology at Jacobs. I'm also the current chair of the Hydrogeological Group of the Geological Society, and I consider myself more towards mid rather than late career, part due to age and in part due to the government's policy on pension ages. There we go, excellent. So, groundwater, why is it important? I mean, the main thing is, it's very hard to find a job where you're working below the ground and you don't encounter groundwater in some aspect or some way on your project. So the 2 main things you need to consider when it comes to groundwater are what's impacted, how's it impacted? How do you address the issues there? There's also a third part to that, which is actually getting people to listen And the first two are generally easier than the last one, because even if you have got the right answer, best advice for a client in the world, it's sometimes very, very difficult to get people to actually listen to your expertise and have a voice at the table. In terms of actually what you're telling folk about, you know, we're considering big structures, large footprints, large surface area, going down to depths. You're going to have to manage water during building of infrastructure projects or development or energy infrastructure. As well as that, you're also going to have to consider the long-term effects. So if you've got water that's present when you're building a thing, you need to manage it, you need to keep it out of your excavation, you need to physically remove it. And Martin will come on to cover a lot of this in more detail in due course. But you also need to consider the longer term, you know, what's going to happen when you've finished that and you've put your structure in place and it's going to be there for tens of years. You've suddenly put a large barrier in place in the ground. So actually putting your development, your activity that you're doing into context of the environment and considering what effect it's going to have, how the environment shapes what you do and how you approach that project is really important. And there's, you know, the two sides of that are learning from, you know, established practice and how to do this, and also trying to frame that in how we can improve what we do going forward with groundwater. So we need to cover what's impacted and how. You know, you're doing construction dewatering, you're pumping a lot of water out of the ground. You need to consider the setting of your site, your activity, choosing appropriate methods and control techniques. You know, what's the timescale that you're doing this over? What's the site setting? Where are you? I mean, I do a lot of work in nuclear new build, and I think there's a standing rule that if you're going to build a nuclear power station, it needs to have a really sensitive SSI wetland right next door, because they all seem to have that. And it puts a massive constraint on what you do to actually do your engineering works on this. You know, you come along and you look at a problem in isolation and you can come up with a perfectly mathematically valid solution, which is great. But then you try and implement it in the real world and you come up against all sorts of regulatory barriers or soft barriers to doing that. And so it's really, really important early on when you're considering groundwater in your project to actually put the project into context and make sure that what you're doing is appropriate. And as I say, once you've built your thing, you've got the same receptors that are there, you know, but now you've got a large barrier to flow. So you might have damming effects, you might change the direction of flow of groundwater locally, and that could cause issues in the longer term. You can interrupt connectivity of groundwater systems. You can add potential contamination pathways by your solutions. If you've got a passive groundwater control system, for example, that's there in the long term to manage poor water pressures, that's great. But suddenly you've got something that transmits potentially contaminated water much more rapidly than would otherwise be the case. So you need to consider all of these things in context. So how do you actually go about doing this? You know, how do you address these issues? And the big thing is to actually determine what you're building, how it interacts with the environment, and how you address that. I hate the word holistically, but I've yet to come up with a better word to try and describe it. So putting everything together. And the first step to this is actually conceptually understanding your groundwater flow regime, hydrochemistry, how the system's functioning before you've broken into the ground and started to build something there or try and influence it. And that helps, you know, what's gonna change, what's an acceptable change, what's an unacceptable change, what methods you're going to use, what sort of philosophy you're going to go down for your groundwater management solution. And a big part of this is actually having enough information to make an informed decision. Often think that what we do isn't so much designing things as reducing uncertainty to an acceptable level when we're dealing with groundwater. You know, how far is enough to get a good enough answer to the question that we can implement something safely without having an unacceptable impact on the environment. I say that, you know, the aim is to sort of prevent or limit the scale of what we're doing here to an acceptable level, and that's going to change depending on what the project is that you're looking at the scale of the works that you're doing and the site setting, and also considering unintended consequences as well. You know, you put in a system to address one question, but if you've not actually picked up all of the other aspects and all of the other things that's going to influence, you can find yourself actually causing problems that you didn't anticipate, and then you're in the really quite awkward position of trying to fix things on the fly. And it's never good when, you know, you tend to do your worst design work and sometimes your best design work when you've got to come to an answer very, very quickly to avoid an unacceptable, potentially permanent impact. And the final point on there, which I'll sort of expand on a bit more in due course, is the sort of future-proofing aspect of this. And it's becoming a bigger consideration now. It was lightly, loosely considered when I first started in practice, but now it is becoming a much more fundamental consideration in developments is how do you incorporate climate change into your designs and groundwater management philosophy. So a bit of the sort of past, present and future on there. There's a picture up there on my left, your right, of the Kilsby Tunnel, and that's a railway tunnel. I think it was probably the first considered groundwater dewatering scheme. So the first sort of properly, vaguely designed system for groundwater control. And, that's a great example of Victorian ingenuity or, sort of engineering coming into practice. And that was really good. And there's a lot of examples, I fell foul of this sort of illusion that the Victorians were fantastic engineers, because look at all this stuff, it's still standing up, until someone pointed out that the things that they designed badly fell over, so they're not there to see. So you get this kind of survivorship bias in your perception of how things work. At the other end of the scale, you've got the Line, which is an exciting project in many respects. It's one of the Saudi gigacities that they're looking to develop. And that one, they're currently building a new marina as part of this development. And that's about 30 meters below ground in a coastal setting in the desert, load of body deposits, so really variable continuity, different layers and all this sort of stuff in there. A couple of kilometers by a couple of kilometers long. Biggest dewatering project in the world at the moment is the claim that they've got on it, and I think they're probably not wrong there. And it's, the stated ambition in one of the early meetings for that is that the design life for this is going to be eternal. It will be our pyramids. It will never fail. So, I'd imagine there's a similar mindset and a similar philosophy applied to both of these kind of eras. It's just, whether that will be standing again, in an equivalent amount of time is another question. But yeah, a lot of the, what this means for us is a lot of the basis for the, the design that we use, observed relationships, empirical relationships, kind of characteristic values, and how you kind of pick something that's effectively a representative measure of natural properties. There's a bit in Eurocode 7 that requires the selection of characteristic values to be complemented by well-established experience. And I think a big part of the challenge that we're going to face around groundwater is that we've got a really good history of understanding it and knowing what happens when you apply different stresses to systems, and true across probably geotechnical engineering more widely. The problem comes is, how do those change as you move forward? How do those values, what is a representative value for a property or a behavior as you're in a different environment, you're having different stresses applied to systems? And there's a lot of talk about a lot of these old infrastructure and aging infrastructure failures, and part of that will be due to inherent material deterioration over time, but also part of it will be because it's suddenly coming under a stress that it wasn't before. So suddenly the Victorians look like less good engineers, even more so, because their stuff starts failing and you get less of it in the historical record. So yes, that's part of the challenge that we face going forward. The flip side of that, of course, is that you don't want to go too conservative in your design, because then suddenly you price yourself out of being asked to offer advice to clients, because anyone can build something that's definitely going to stand up. It's just that it's going to be so over-engineered it ceases to be economically viable. So it's finding that kind of balancing point and how to apply that knowledge. Historically, when sort of groundwater has been considered on projects, it's been sort of brought in to address potential issues. Try and de-risk things, increase design certainty, save money, build it faster, all that kind of thing. And as we move forward, I can see that that's still going to be the case. Those will still be drivers for the involvement of people applying geotechnical engineering and groundwater control and management. But also going forward, we're going to have to address things like integrated design, how to properly carbon budget for projects. Simply throwing in a big concrete cut-off wall is not necessarily the right solution, because there's a huge amount of embedded carbon in doing that. Is there a more efficient way to manage that you can exclude groundwater and manage it more efficiently, manage it sort of as a joined up system? And again, things like circular water economy, I've lost count of the amount of projects I've worked on with big dewatering ask over there, and over here you've got a huge water demand, and the two sides of the project never actually speak to each other. And there's, you come up with a solution that might work about, well, you could use this for grey water, you could use this for ambient cooling before you discharge it out to sea. And the answer always comes back, that's a really good idea, but it's too late now because it's too far down the design process, we can't do that. So I think one of the big challenges for this is going to be being part of the conversation early enough that we can actually influence people's thinking about how we apply geotechnical control for groundwater in a sort of more considered fashion. There's a list of challenges up here that I was kindly provided by a contact I've got at the BGS. And there's a wide range of stuff up there, and it's not just groundwater specific, but I think it's part of how we apply what we do in a changing world is going to be that you need to apply our knowledge and our very specialist knowledge in the context of these challenges, and actually demonstrating that our understanding can help tackle a lot of these problems, and actually genuinely add value and help develop a sustainable future and sustainable solutions. And in terms of the future challenges as well, I can see that there's a big problem coming forward here, and everyone's sort of got this thing about AI being a major problem for the future. And I always thought, I felt quite smug about this. I was like, I'm a specialist, me. AI is not coming from my job. I'll be fine. I know all this stuff, and I need to apply judgment to what I do. And that's where AI falls over, because it's largely learning from what's out there and just regurgitating it in a fairly credible sounding sense. But actually what we've got is that we have a long history of application of what we do as a practice. So AI's got something that it can lean on that actually, to the layperson or to even an educated client who doesn't actually know the details of what we do, they could look at that and go, well, that looks like what you've produced, And actually also now, the first bit of the puzzle, collection of data, there's lots and lots of different ways now that, some of the data collection techniques that we deploy routinely on projects now were science fiction territory when I started out, and I'm not that old, I hope. But it's, those are now commonplace. So you're going to have people who can get hold of loads of data relatively cheaply, and then they can put it through an AI interface, without any guidance necessary, just produce me a report using this. That's what I pay these guys to do. And then you can bung that into some design software that will spit you out an answer. And you'll go, expert's report, my report. Well, this one was much cheaper. I'll have one of them, please. And you might get away with it a few times. And then you're back to where we started out with, sort of finding rules for geotechnical engineering, which is stuff starts to fail. But the hard part that we're going to have as practitioners in sort of managing groundwater, and why I think it's so important, particularly with groundwater, because it's an area where even within the technical discipline, there's a degree of nervousness about it's a bit difficult, it's a bit complicated, it doesn't really behave like I think it should. So within the science, within the profession, there's a bit of nervousness about actually engaging with groundwater appropriately already. How we then convey our collective knowledge to client organizations and stakeholders to make sure that they're not misled by seemingly credible information, and actually demonstrating that our value as specialists is worth paying for. And I can see that's actually probably going to be one of the bigger challenges rather than the technical challenges in terms of how we manage a changing climate and selecting values and dealing with different nature of uncertainty. We can adapt to that because we've adapted the science as we've gone on by learning from what's gone on in the past. But I think that how we actually continue to demonstrate that specialist understanding and get people to buy into that and place reliance on the experts like the people in this room, I think that's going to be the big challenge that we face going forwards. But yes, I shall wrap my little bit up there about why I think groundwater is important, and so I hand directly over to Martin, and then oh, William, sorry, William, sorry. I skipped William out, sorry, William.
Thanks. Well, good evening, everybody. I guess that I'm what Emily euphemistically referred to as late career. What I would say is that from my perspective, it doesn't particularly feel like that. I'm still finding out new stuff, and I'm absolutely sure that when you all get there, you'll feel the same way. Let's see if I can work the technology. Oh, yes, okay. So I felt a little bit embarrassed about doing this because my bits of the MOGE are what you might call Groundwater 101. So we talk a little bit about the groundwater profiles, the importance of developing a conceptual model. So what are the strata, what are their hydraulic conductivities, what are the boundary conditions? Then we look at a couple of sort of fairly well known and well established analytical techniques, steady state flow by drawing flow nets, and hopefully you remember what flow nets are. So that's all based on Darcy's law. And then the second thing is transient flow, So that's consolidation or heave in response to a change in total stress. And that's particularly relevant when we're looking at clay soils. I mean, in principle, it will happen with any soil, but it's just that sands are very stiff and very permeable, so there isn't much of it and it happens really quickly, so we tend not to bother about it. So I'm not going to talk about Groundwater 101, but I am old enough to have vinyls or records, as we used to call them. And looking through the collection, I came across this, which is great hits you played when you were young. And they are such things as Fur-Elise, Paderewski's Minuet, and so on. And I kind of thought, well, yeah, okay, but did we really play those things on the piano? Or did we listen to our teacher playing them and sort of falsely remember that we learned them? And there was always that tricky left-hand passage in bars 28 to 32 that you never quite got right. So hopefully it's always a good thing to sort of remind ourselves about some of the basics. So the first thing that I'm going to have a look at is how can we apply some of these simple techniques to a couple of real-life problems. So the first one is the Silvertown Tunnel cross passage dewatering, which WJ carried out. And actually, Emily wrote or co-wrote this article, but she says her name is just in little letters right at the bottom. So there it is. So if you look at the top right of this screen here, so there's the laser pointer, this is the sort of cross section through the cross passage. And the next view just shows a sort of idealized version of that. So we've got London clay, Lambeth group sands, and then below that we've got Lambeth group clays. And the idea is that we dewater for the construction of the cross passage by putting in a series of well points from the right-hand tunnel. So I didn't get involved with the calculations of this, but Toby Roberts very kindly lent me this, because when I set my end of module exams, I quite like the question to be based on something which is novel and something which is real. So I decided I would set this as a flow net, and that's what I did. So the first thing is that we're only really interested in what's going on in the sands. The clay above and the clay below we can assume are effectively impermeable. The second thing is that the sands are anisotropic, so we have to shrink the horizontal dimensions to draw a flow net by the square root of the ratio of permeabilities. So they're shrunk, I think, by a factor of root 4, which is 2. And then the way that we draw a flow net is we identify, well, where is the water going to? So it's going to this dewatered zone here. Where is the water coming from? So we say that it's coming from some fictional distance of influence, which we've taken here as a certain distance away. What are the bounding flow lines? Well, it's got to come along the impermeable interface. It hits the tunnel, which we assume is impermeable, goes around there and then finds its way eventually to the sink. And then similarly, the bottom flow line will come in like that. Having identified the source and the sink, it's then simply a question of filling in the space with a network of these so-called curvilinear squares. And you calculate the flow rate per meter run of the problem by simply looking at how many flow tubes have I got. I've got 1, 2, 3, 4. How many head drops have I got? I've got 1, 2, 3, 4, 5, 6. So it's 4 over 6 times the overall head drop times the effective permeability. And that gives us the flow rate per meter run. Now, I didn't use the real parameters. So the real parameters in my exam question were that we had a drawdown of 8 meters. We had a transformed permeability of 5 times 10 to the minus 6. The dewatered length was a linear meter. And I calculated that as the flow rate in liters per second. Now, the real situation had actually got a rather bigger drawdown and a rather higher permeability, and it had a dewatered length of 20 meters, and that gave us a real flow rate. This is the measured flow rate of 6 liters per second. But the important comparator is actually the dimensionless flow rate, which is the actual flow rate divided by the permeability, divided by the head drop, divided by the length. And you'll see that from my flow net, it came out as 0.675. And the actual one, depending on how you take the permeability, was between 0.6 and 1. So the simple model actually gives us not a bad representation of what goes on. It has forced us to think about where is the flow coming from, where is the flow going to, what are the bounding flow lines, and we can get quite a good visualization of what the flow looks like. Even if you then run it through a seepage program or a finite element program, if it's not giving you an answer, which is something like your flow net, then there's probably something wrong with the way you've set up the program. Another one that I set as an exam question, which I won't dwell on too much because this was like many things in sort of environmental geotechnics. This was about dewatering, or the potential dewatering of a tailings lagoon. So tailings is the sort of waste product that you get from a mining operation. And the idea was that it had come as a slurry down this discharge pipe. So it had settled out in 3 zones, with the high permeability, the coarser material dropping out first, the intermediate permeability material dropping out here, and then the slimes or the very low permeability up at the base. So the idea was that the students were given the D10 size and the horizontal and vertical permeabilities of each of these zones. What they had to realize is that actually zone 1 is effectively very highly permeable, so we can treat it as an equipotential. Zone 3, which is the slimes, is very low permeability, so we can treat it as impermeable. So all we really need to do is to worry about the flow in zone 2. We've also got anisotropy, so we have to shrink the cross section. And then again, we have got basically the equipotential from zone 1, the flow through the zone of interest, which is zone 2, and then this is the well point dewatering system idealized as a line, and the low permeability of zone 3, and then we can get an estimation of the flow rate. And I think there's at least one person in the audience who's probably now at this stage having nightmares, because I think this was on their end of module assessment. So apologies for that, I'd forgotten about that, but there we go. I can't compare this with any real data because, like many things in environmental geotechnics, I don't think they've got any intention of ever dewatering this tailings lagoon, but they have to show that they have got the option of doing it should it become necessary. So that's flow nets. So it's covered in a little bit in the MOGE. And if you want a better explanation, I would refer you to my textbook, Soil Mechanics Concepts and Applications, as I would. Not that I make much money out of it, I can assure you of that. Right. Second thing is consolidation, so transient flow. So this is a well-known high-speed rail project that I first got involved with probably about 5 years ago, when costs had started to get a little bit uncomfortably high. So what happened was that a series of pilot studies was carried out, where, working with the design contractors, we sat down, we looked at the preliminary designs for a number of typical earthworks, embankments, cuttings, retaining walls, and we looked at them and said, well, okay, how can we hose out some of the cost? Now, there's a little bit of an aside to this, that if you look at the total bill for constructing this infrastructure, my guess is that it probably breaks down into roughly a third for kind of planning and legal fees and acquisition of the land and stuff like that, possibly a third for the civil engineering works, and maybe a third for the kind of signalling and trains and that sort of thing. So in some sense, the thing that is going to last your 150, your 200, your 1,000 years is actually the infrastructure. So there's an interesting question about whether it's really worth hosing out 50% on the infrastructure if it will only really save you 15% of the project overall. Not that that is an excuse for engineers to be profligate and for engineers to design stuff, as Mark was saying, that's too expensive, so expensive that it never gets built. And that does ring a little bit of a bell, doesn't it? So anyway, we have a look at this embankment. And what's all of this stuff below the embankment? So this is the embankment itself where the railway runs. Because the material that's excavated from up the line is not of sufficient quality, and because the people who live in the Chilterns don't really want to be disturbed by trains running through their backyard, we pretend that our embankment is actually in a cutting. So we put in this landscaping and noise reduction berm. And the first thing you notice is there's all of this concrete below the embankment. Why have you got this concrete below the embankment? Well, because the maximum allowable settlement is 30 millimeters, and our calculation says it's going to be 32. Really? Well, how did you do the calculation? Finite element analysis. And when did you start consolidation? After we built the embankment. Well, we know that with consolidation and swelling, it happens quickly at the start. So if you pretend that nothing's happened for the first year or 2 years while you're building the thing, then of course you're going to over predict the actual amount of settlement or heave. So my line was, well, I could do a slightly different calculation that said 28 millimetres, then we wouldn't need any concrete at all, would we? And there was a sort of begrudging acceptance of that. So one of the things that was going to happen anyway was that they were going to build a trial cutting. So there's the trial cutting and a trial bit of an embankment. And they were going to see how long did it actually take for the soil to respond to the building of the cutting, so the excavation of the cutting, the building of the embankment. So that took place at a place called Boddington, which is just here, just north of Banbury. And that's a close-up which shows the view of the cutting, view of the embankment. I'm just going to say a little bit about the cutting, and in particular, we've got these arrays of piezometers at different depths below the cutting. The next view is actually, this is a picture of the trial cutting itself, so there it is. And this is the geology. So we've got the cutting depth of about 13 meters. Then we have the mudstone, the Charmouth mudstone, a band of limestone, and then below that we've got mudstone. The stuff that's excavated is clay. So we excavate the cutting down to sort of this level here, and what's probably going to happen is that drainage is going to be vertically to the surface and down to the limestone. So that's probably how this band of mudstone is going to consolidate. So the pore water pressure measurements are here. So this is the change in pore water pressure as a function of time during the period of the trial cutting. And these are at various depths below the floor of the excavation. So you can see that this is the excavation period. So you can see there the response of the pore water pressures. And then excavating the cutting actually changes the equilibrium pore water pressure. But what we can see is that we have reached the new equilibrium within something like certainly 3 to 4 years. So 1,280 days was our estimated time. Now, okay, the people doing the original calculation didn't have the benefit of this knowledge. So how does it compare with information that would have been available? So we're looking there at an equilibration time of around about 1,300 days. So from laboratory tests, from triaxial tests, high quality triaxial tests where we can measure the shear modulus, we know that the shear modulus or the Young's modulus, whichever modulus you want, it depends on the strain. So we won't take the G0, we will take the shear modulus at 0.1% strain, assume a Poisson's ratio of 0.3, and that gives us an effective one-dimensional modulus. So that's going to govern how much heave or how much settlement we get. Assuming that we've got two-way vertical drainage of that upper band of mudstone, that gives us a maximum drainage path length of 9.5 meters, and the actual consolidation time was about 1,280 days. Now, we know that consolidation is complete when the dimensionless time factor, big T, which is CVT over D squared, where CV is the consolidation coefficient, which is K E dash naught over gamma W. T is the elapsed time, and D is the drainage path length is equal to 1. So if we put that back in, we can infer a field vertical permeability of about 2 times 10 to the minus 11 meters per second. And that compares with 10 to the minus 10 and 10 to the minus 12 measured in the triaxial cell in the odometer. Now, I know it's a bit of a cheat because it's a logarithmic scale, but the point is that it is not a million miles away from what was measured. And actually, a bit of engineering judgment and the simple model would have told an awful lot about what the consolidation or swelling time of this was going to be, and therefore whether we needed to be worried about whether it was 28 or 32 millimeters. And this was an article in Ground Engineering, I think the last issue or the last issue but one. There was a whole thing about these earthworks experiments in HS2, and yes, they did get rid of all that concrete. They got rid of all the concrete below the embankments. They got rid of the similar concrete below the cuttings, where they were going to have rafts, concrete rafts, held down by concrete piles to prevent problems associated with this heave that was going to occur. And actually, all of it was got rid of, which is great news. That's wonderful news. So to conclude, and I pay a little bit of homage to Syria Report C750, which is the Syria Guide to Dewatering, which was written by Martin, Toby, and myself. So in geotechnical engineering, it is necessary to make simplifications to develop a conceptual model. The conceptual model has got to be amenable to analysis, and a successful model has got to take into account every relevant factor. But you don't want to cloud it all with lots of factors that are irrelevant. And you certainly don't want to introduce things that are demonstrably wrong because you couldn't be bothered to think about whether they should be included or not in the first place. So sometimes people say all models are wrong, but some are also useful. And going back to Mark's challenge about AI, you know, actually the challenge for the engineer is not to produce something that's going to cost 10 times as much or the same as the AI. We have got to actually get a little bit bolder about understanding what's important, what isn't, and not completely over-engineering things. Otherwise, you might as well hand over to AI. A complicated analysis cannot compensate for a flawed conceptual model or a lack of realistic parameter values. You are far better to do a simple analysis with decent parameter values with the right conceptual model. And you know, I think there is a bit of a tendency to rush to an FE analysis, plug in all the numbers and see what it says. It is not a substitute for thinking. The thing that we can do that AI can't is think. So think about that. That's an important thing. So it's better to undertake a simple analysis based on the right conceptual model and realistic parameter values. And the other thing is that simple analyses make you think about what is the conceptual model in a way that just sort of plugging in the numbers into an FE analysis don't. So I think on that note, I shall hand over to Mark.
Thanks, William. I feel obligated to talk about where I am in this spectrum of early and late career. And I would say, look at the data. And the data is, William Powrie was my PhD supervisor more than 30 years ago. And I gave Mark Lee his first graduate job more than 20 years ago. So I'm clearly in the middle. But I suspect I'm more at William's end. But the whole point is that I make mistakes. I try and make sure those mistakes aren't catastrophic or serious, and then I learn from them. And ideally, I would like to think that I share with people my mistakes to try and improve things. And I'm trying to talk to you about if William's done, let's say, the concepts and Mark's done the background, I'm going to do a bit more practically based. I'm going to talk about chapter 80 on ground control that I was the author of, but I also want to touch on some of the other aspects in MOGE. So I was quite pleased as an engineer to realise that volume 1 of MOGE has precisely 50 chapters, a nice round number. Sure, that didn't happen by accident. It's designed by an engineer. And volume 1 is called Geotechnical Engineering Principles, Problematic Soils and Site Investigation. I think within that, it's a cliche, but it's a true cliche, that groundwater is relevant to almost every aspect of geotechnical engineering. But I think particularly within volume 1, chapter 18 on rock behaviour, because it's sort of implicit what we talked about, in soils, groundwater broadly flow is intergranular in the pore space between soil grains. Because in rock, typically the groundwater flow is through fractures and fissures. The chapter on ground investigation is relevant, and I'm going to talk in a minute about groundwater monitoring wells, because determining groundwater levels is pretty important. And then also, we've talked about permeability in times, and we need to try and determine that permeability in some ways. And chapter 47 deals with field geotechnical testing, including permeability testing. So I want to talk a little bit about monitoring wells, ways of determining the groundwater level, because we need to know groundwater levels and groundwater pressures for design. And William used the term piezometer, or as I say, piezometer. But the point is, terminology is really important, because not every monitoring well is a piezometer. And I want to talk about the difference. So this diagram here is a standpipe. And so if you drill your investigation borehole and you put in a perforated pipe, and you essentially have a single set of perforated section, and you have a long response zone where the perforated pipe is surrounded by sand. We have a bit of grout seal at the top to make sure the surface water doesn't flow in. But essentially, you can see here that this piezometer, that this standpipe, rather, I'm telling you, this standpipe cuts across multiple aquifer zones. And so it's going to give you a hybrid water level that is essentially a weighted average of the water level, the water pressure in those zones. And the water level in this standpipe probably won't be representative of either aquifer zone. And if you're trying to design, say, a retaining wall, look at the porphyry distribution, it's not going to give you the answer. You actually need to have a standpipe piezometer, which is a designed device because you've installed it with an intention of targeting a particular permeable zone. In this case, we've got a short response zone targeting aquifer 2 here, and that will give, if it's correctly installed, a water level or water pressure corresponding to that aquifer zone. And obviously then you would need to have perhaps a separate borehole targeting this zone here. But so a standpipe piezometer is something that's designed and it's going to give you the water pressure or the water head at a certain zone. Of course, nowadays we increasingly use electronic devices, and you can choose to have a fully grouted piezometer installation where you can have multiple pressure sensors installed in different zones. And here, this single borehole would allow you to get electronic data that can be calibrated and converted into water levels for different levels. So terminology is really important. And I want to move on to volume 2 of MOGE, which is called Geotechnical Design, Construction, Verification. And again, I was disappointed to see that this wasn't also 50 chapters. But I do wonder whether it was designed to be 50 chapters and some scope creep happens, and chapter 101, which is how the book ends, came into it. And there are various sections in this, and this chapter is called Geotechnical Design, Construction, and Verification. And I just want to touch briefly. Earthworks, obviously, is significantly affected by water in general and groundwater in particular, and that's covered in the book. There's a section on construction processes, and I'll shortly go through my chapter 8 on ground control. And then there's also construction verification, which ties in with William's thing on instrumentation, you know, figuring out what we've actually achieved and how we're going to do it. And that section deals with monitoring and instrumentation. So I'm to talk briefly about groundwater control, and the definition we use for groundwater control in MOGE is groundwater control encompasses the range of temporary works techniques used to allow below ground construction projects to be carried out in dry and stable conditions. And I don't propose to go through the chapter specifically. I want to talk about the why, the what, and the how. The why is what problem do we have, which problem we're trying to deal with, and that comes back to understand the conceptual model, understand the construction processes. The what is, what are we going to do about it? What objectives do we need to set to deal with this problem? And the final part is the how, is what methods and techniques should be used. And I would argue the how bit comes very much at the end once you understand the problem and what you need to do about it. And the reason I put it like this is I argue that you can apply this approach to almost any geotechnical process, because you need to understand why you're doing it, you understand what you need to achieve, and then how you achieve it. So let's look at the why part. It's all about the conceptual model. And William touched on this in a very similar way, and we hadn't confirmed it before this, but you need to develop a hydrogeological conceptual model relevant to the ground control problem to provide the information necessary for design. And if the conceptual model is a poor match to actual conditions, all the subsequent design work, no matter how sophisticated, is likely with little value because you're just not analysing the right thing. The other thing is that when you're formulating a conceptual model, if you're feeling uncomfortable, if you feel there's insufficient reliable data to form a convincing model, that should trigger you really to communicate forward, and it should be assigned further site investigation. Perhaps specific investigation targeted groundwater might be needed. In terms of the factors relevant to conceptual model, the aquifer types, and aquifer being typically the term we use for a water-bearing zone in the ground, the aquifer types and properties are relevant, but also the conceptual model isn't just about the geology, it's about what we're trying to build. You know, if you're constructing a shaft 100 meters deep, that's different to a pipeline, 5 meters deep, and the size and lateral extent is important too. The soil and rock permeability is really important, and of course it's quite difficult in many cases to actually measure or obtain representative values of permeability. And finally, aquifer boundary conditions, including the presence of aquitars that might divide aquifers up, that's quite important too. So the next part is the what, the objectives, what we're going to do about it. And there are probably 3 objectives worth talking about for groundwater control. And the first of them doesn't even deal with groundwater. The first situation is you need to do with surface water. You know, in the UK, for example, it rains from time to time, and when you dig an excavation, unless you're very careful, your excavation is going to act as a sink or a sump for all the water in the surrounding area. This is a picture actually from the Republic of Ireland, and to get a scale for it, that excavator is a large 45-ton excavator, and that's a 6-wheel drive Volvo dump truck. The tires of the dump truck are probably about 2 meters diameter. You can see that there's at least a meter of water, a meter of surface water in there, because this is quite a low permeability soil in glacial till. And you can see here that not controlling surface water is going to be a massive impediment to construction on this project. If we talk about groundwater, probably the most obvious thing in terms of the objectives that jumps to people's mind is we need to prevent the excavation from flooding by groundwater, something that's failed to be achieved here. You've actually got a sheet pile cofferdam going around here, and you can see it's flooded, and some pumps here to try and stop it flooding even more than actually is there. But in my experience, and this is one of my problem jobs, by the way, that I'm graciously sharing with you all. In my experience, flooding on this scale is actually quite rare because the instability problem I'll talk about in a minute occurs before this happens. This project is very interesting because this excavation flooded on multiple occasions, and broadly speaking, it was flooded by a water source that wasn't expected. So I would argue this is a straightforward failure of the conceptual model, and the various works that put in place were potentially acceptable to the conceptual model they had, but didn't actually weren't relevant to the situation in the ground. But as I said, the actual main geotechnical problem from groundwater is the excavation becomes unstable. And here, if we imagine we're looking at an excavation in a silty fine sand, maybe a beach deposit, and we're going to do a battered excavation where there's a sloping side, and that dotted line shows the slope angle that you would get if the soil was essentially dry. And it's not dry, we've got a water table here, and the excavation being made, and they're pumping water with sump pumping. And this, in a fine sand, this sump pump might be quite a small pump, because as I've said, the inflows are probably so small, you're not going to actually flood the excavation out very quickly. Long before the excavation floods, you'll get instability. And what actually happens is the water flows inwards on these flow lines that you could do a flow net for should you wish to give yourself nightmares. And the flow line comes in, you see above the lower groundwater level, the excavation is broadly stable at roughly the same angle it was before. But as soon as the groundwater flow line intercepts the slope, the stable angle reduces dramatically. And there's a rule of thumb that if you have horizontal flow through a slope, the stable angle reduces by about 50%. So if you had a slope that was stable in the dry at, say, 20 degrees, if you get horizontal flow, that would reduce to about 10 degrees. But it gets worse than that. If you get down towards the bottom of the excavation, some of these flow lines in your flow net are coming almost vertically upwards. That implies that in the bottom of the excavation, you've got low total stress, high pore water pressures, you get nearly zero effective stress. And this condition known as quicksand or running sand will occur. And the excavation becomes so soft you can't even stand on it, and plant will sink in. There's another form of geotechnical instability, and that's where you have layered ground or these low punctured layers called aquitards. So here we've got our same battered excavation, and we've dealt with that slope instability problem, and we've put a system of shallow wells known as well points, and we've dewatered this section here. But below the well points, there's a low punctured layer, and this low punctured layer acts as a sort of hydraulic separation layer. And it means the dewatering effect of these well points is not effective down here. So you get the high pore water pressures here in an area where there's low total stress, you get heave, upward movement, and eventually you get what's known as a blow, where you get a rupture and you get uncontrolled water inflow. And again, I would argue that's a failure of the conceptual model, because if the conceptual model identified that this layer was here, they'd either deepen these wells or possibly give it some relief wells. So here we've been talking about the what part, the objectives. So now we get to the final part, which is the how, the methods and techniques. And broadly speaking, ground control methods and techniques fall into two groups: the pumping method and the exclusion methods. So this is a system which shows a ring of pumped well points around an excavation. And this is an example of ground control by pumping, where we put an array of wells or sumps in or around an excavation. We pump collectively from all these wells or sumps, and the collective lowering of the groundwater level, hopefully, essentially means your excavation that was previously below the groundwater level is now above the lower groundwater level, with all the stability improvements that gives. So here we have all the wells around the outside are pumped. The ring of wells will continue around out the screen. We pumped away, and we're lowering the groundwater level in this way. The alternative method is ground control by exclusion. In that case, we're essentially trying to keep the water out. So in this case, we've got our excavation, and we've constructed a physical cut-off wall, perhaps a cement bentonite cut-off wall, that goes all the way around the excavation. So imagine it coming out of the screen and forming a complete barrier. And then at depth, we have a low penalty layer, maybe a glacial till or maybe a mudstone. And the combination of the artificial vertical barriers and the natural subhorizontal stratum at depth means we've effectively isolated our excavation from the wider groundwater regime. We still have to deal with the trapped water inside the excavation, It's quite a small quantity. We can sump pump that away. We pump a much smaller quantity of groundwater than for a pumping system, and we lower the groundwater level. And importantly, we're hardly lowering the groundwater level on the outside. So if we're worried about external impacts, these exclusion methods can be very attractive. And my final point is that the various detailed techniques to apply both pumping method and exclusion methods, they're not interchangeable. That particular pumping method and particular exclusion methods only work in certain types of ground conditions, at certain depths, and in certain types of permeability. This diagram here is in MOGE, but it's from Survey Report C750, and that's the range of application of pumped well methods on drawdown and permeability, and this is exclusion methods against permeability. The point being that you might get a good conceptual model, you might then do good analysis, you might specify a system. Let's say you want to have a cut-off wall around a structure, and you want a secant pile wall 80 meters deep. I can tell you that you cannot install a secant pile wall to that sort of depth. You can design it and you can specify it, but it's not going to get installed. Similarly, you could look at designing a well point system in a permeability of 10 to the -7 for 10 meter drawdown. You can design it, it's not going to work. So I sometimes say you don't need to understand ground control methods or any other improvement methods at a nuts and bolts level, but you need to have a conceptual understanding of the application and limitations, because ultimately, and I think we've all said this, everything we build needs to be constructible, and that involves time, money, safety, environmental impacts, and overall economics. So that's the end of the scripted part. So I think we're handing back to you, Emily, is that right?
Okay, thank you very much, all three speakers. So this is where the floor opens up. So if you haven't already put some questions on Slido, please do. Or if you want to be brave in the room, put your hand up. I was thinking when I was putting this slide pack together, and I've been scribbling some notes now, what sort of the key discussion themes might be, and things that popped into my head with all of these presentations. I obviously picked up on the importance of terminology. I think we've all made mistakes probably in our professional careers. And it's really important when you're maybe discussing things with a client that they exactly understand what you were on about, and vice versa from the other way around. Conceptual models was definitely something for me that came through with all of those talks, and how we can produce those and how we can make sure they're the best model that they can be. Adaptation of knowledge to new challenges, and I guess by extension, circular water economy, sustainability, climate change. There's a whole heap of problems and maybe opportunities that our industry, especially related to groundwater, may face in the future. So if you've got any questions or anything completely different to that, I encourage you to put them in our Slido. I think we've got some questions already. And can I ask our speakers to come up to the panel? We have a roving microphone for those online. I'm not sure how this works. Are you going to test to see if this is working? Can you hear me? You can't hear me. Can you? Oh, wow, that's loud. Will that be heard through Teams?
When it's green,
yeah,
means it's on.
And that could be heard through Teams as well, yeah?
Oh, yeah, absolutely.
Okay,
so
perfect. Oh, this is fancy. Okay. So I'm just going to put this here. Well, I guess I can ask the first question actually. Right, okay. And let me get the first question up. Right. Oh, this is a big question. Question for Mark. How do you think the concept and application of groundwater control will change over the next 5 years?
Thank you. So for those on Teams, this is the world's smallest microphone. This feels very strange. The next 5 years, I can see actually probably not that much change. I think it's going to be an awareness raising exercise, and I can see there being possibly within the industry a bit more of a change and a change in philosophy and how we go about kind of considering more sustainable solutions. So the exam question will change, I think, over time from our clients, but I think it's almost incumbent on us to start to drive that change ourselves. You know, I've long advocated for joining up the fact that you need to get rid of a load of water from somewhere with the fact that you need a load of it somewhere else on your site. That I find it amazing that no one else can see that these two things are connected in some way. And actually what you've got there is an incredibly valuable resource if you're dewatering a large excavation. You know, you've got a ready supply of something that people are paying good money for. But I genuinely think it's going to be a longer term challenge. So I think the next 5 years will probably be a bit more of an internal conversation within the industry, within practitioners. And then hopefully we can then use that to sort of go out more externally and try and help raise awareness of where we, you know, how we can better help people solve their problems, because a lot of the challenge comes back to, you know, it's ill thought out solutions, or it's what we did last time, or it's something we know will work, and actually we need to get a bit clever about how we answer these problems. And I think it's what William was saying, you know, it's actually pick out the things that are important and will make the biggest impact on the solutions that we develop.
Well, perhaps I can just say that we need to be aware that not every project is a national scale project. So I think, you know, William's talked about HS2 and Mark's talked about some very large projects, but there are a large number of much smaller projects, and I wonder whether there's going to have to be a raising of, let's say, environmental standards on the smaller projects to recognise that whichever jurisdiction in the UK you work in, that regulations are changing, and then getting better about not discharging dirty water and so on. And I came back to communication. People who work for me will know that. Some will say, we're not engineers, we should be in the communication business, and Mark touched on about that, to raise standards and get our clients to understand risks. And I think there's a big communication piece for the smaller projects who don't use companies like Jacobs, for example. So it's maybe for the small and medium-sized consultancies and designers, you know, a bigger role for them perhaps.
So not really to add, but just to emphasise those three things. I think environment, sustainability, circular economy, 4 things, quite like the Spanish Inquisition, this, isn't it? So circular economy, sustainability, environment, and quality. I think quality is really important, actually only doing what's necessary when it's necessary. I think Mark and Martin have summed that up.
Okay, I've got another one here. Martin, for someone doing a preliminary desk study or conceptual site model, what readily available resources would you review before getting any site-specific data?
Well, obviously, if we talk about the UK, we're very lucky that the BGS Geo Index, now it's online, is a huge resource. I mean, given I am at the older end of the spectrum, geological maps, you know, you only had the geological maps your company owned. And I can remember getting the train into London and going to the Geological Society Library at Burlington House and tracing some geological maps because you wasn't colour photocopying. I'm not that old. This was in the late 80s. And of course, never mind the lack of quality, the time scale involved was very slow. And, you know, in the last 10 years or so, with GIS systems being developed and publicly available, you can go online, you can see the geological maps of your site. In many cases, you can find really quite high quality logs for boreholes nearby. So the BGS in the UK is a massive starting point. And then as well, you know, published papers, and all 3 of us published papers to share experience. And if I'm working in a new location, I just Google location name hydrogeology, location name groundwater, and every now and then you get something amazing free hit. And okay, you might need to go online and pay 10 quid or something on the you know, paywall thing, which I do hate, but potentially that value might be huge to your product. And the key element is the speed, because then the really key part about this is, it's right that you need to get all the readily available information before you commit and plan to an intrusive investigation. Walkover surveys, obviously, in non-urban areas are pretty important too.
Okay, question for William. How should the hydrogeological community encourage their graduates to complete flow nets prior to jumping straight into modelling? How should they do it?
So I think it is a little bit, it is the kind of great hits you played or possibly didn't play when you were young. And I think that people get worried about flow nets because they're afraid of making a mistake. And if you like, the whole point of drawing a flow net is to make a mistake, which is why you don't start. You know, if I do the killer Sudoku, I have learned the hard way never to fill it in pen because you always make some mistake, some stupid mistake, and then you have to rub the thing out. So I think, you know, it is really almost encouraging people not to be afraid of making a mistake. And one of the things that I think has happened with us at the university, with COVID, we sort of moved away from the traditional lecturing and we put the lectures online, but we had tutorial sessions. And one of the most popular ones is actually when you get people to come up and show examples of their flow nets to their peers. And initially there's an awful lot of reticence, but as soon as somebody has a go, the dam breaks, and then you start to get that peer-to-peer discussion. So I think really sort of encouraging people not to be afraid of making a mistake. I think also encouraging people to talk about it. And the other sort of interesting thing is actually have a go at trying to get a real problem. How can I simplify this so that I can draw a flow net? So those might be some of the things that would start things off. So perhaps a flow net sketching club would be a good thing to do.
Yeah, I'd like to add to that, and so I worked with William when I was doing my PhD, and I had been taught flow nets at undergraduate level at a different university. And I realize now that I didn't understand the concepts. And it's like a eureka moment. Once you understand the point about flow tubes and head drops, you think I can analyze anything that I can draw. And my challenge to people listening is, okay, you're using SeepW or using ModFlow or something else to look at the flow around a cofferdam or the flow through underneath the dam. How do you know the answer you've got is even in the right ballpark? And trust me, once you have flow nets, you can at least confirm on an order of magnitude level what the flow is. And the really amazing thing that I learned was how repeatable flow nets are. So you can, William had, I think, I took 4 flow tubes in that diagram there. If William had done it with 8 flow tubes, and he would have got, within about 10%, I would guess, the same answer. But you have to do it yourself. There's absolutely a practice element to it. I have certainly, within the last few years, used it to validate a lovely, glossy groundwater modelling report that someone sent with all the colours and everything. But I needed to convince myself that the order of magnitude flow was right. And without convincing myself that, I didn't feel happy to sign off that project.
Fight for the mic now, isn't it? I'm in possibly a slightly different position, again, being slightly younger. I think I fall into that weird sort of crossover thing, which is called the Xennial generation, which are people who came of age when computers also became widely available. So, you know, I grew up in a world without computers being a thing. And then when I was at university, you know, it was like actually a lot of stuff's done on computers, but it was very, very early days. And so there was still that real connection and memory of why you do it longhand. And a lot of the course that when I did my master's was around, you know, like plotting up pumping test results and doing curve matching with tracing paper and graph paper. And, you know, and a few people on the course were like, well, there's software that does this for you. Why are we doing it this way? And the answer, which I think is probably core to this, is by doing it by hand, you know what you're doing. And then when you come to do it with a computer software, you know whether you've got it right. And that's the big thing, is it's that kind of connection. And and again, it might be slightly biased here because I tend to learn, you know, I tend to retain information better when I write handwritten notes than I do by typing it. And that's possibly an inherent thing, possibly because I grew up in a world of writing notes by hand, and that's where my brain's wired. And I appreciate that the world is no longer that world, you know, it's not that setting anymore, but I still think the value of doing it by hand gives you that real connection with the problem that you're trying to solve. And when you make a mistake, you see you've made a mistake, rather than the software that's a mathematical thing that will give you an answer that is mathematically correct, but perhaps conceptually invalid.
I mean, I guess I'm not actually a great mathematician,
but I think the physics of a problem is always more appealing to me. And you know, I think I say in the preface to my book, it's a physical approach. It's getting the physics right and trying to keep the maths as simple as possible. And for me, I think that's the thing with flow. You know, a flow net is actually a solution to not a particularly complicated, but to a differential equation, the Laplace equation. But what it forces you to do is to think about the physicalities of the problem. I was also quite fortunate in that one of the people who helped me with the flow nets in the book, so there's actually quite an interesting article by Eddie Bromhead where he kind of critiques flow nets in various textbooks. And you've got to beware because there are quite a few textbooks where they are wrong and they actually repeat mistakes that have been in other textbooks. And Eddie Bromhead in his article points that out. But I was lucky in that a chap called Richard Harkness, who had actually been a demonstrator in Arthur Casagrande's FlowNet course at Harvard in the kind of 1950s. He checked all of my FlowNets in the book, and Richard was a great sort of aficionado of FlowNets. But Martin's absolutely right. You get this eureka light bulb moment, and you only get that by practicing. So you have to practice, you have to talk about it, and you have to actually enjoy the creativity of when you see this thing. One of my great bugbears with numerical analyses is that they give you equipotentials or contours that could be equipotentials on a flow net, but they're not because the spacing isn't right, the spacing isn't chosen. And for me, that visualization of the flow tubes and the head drops, or if I'm doing a stress analysis of the lines of maximum shear stress, the characteristic directions in a stress analysis, for me, that's an important part of saying, yeah, I can see that, and that all sort of makes sense with all of your mental experience. I've got no problem if that comes out of an analysis, but usually the computer software isn't really geared to giving you the information in that particular format.
Thank you very much, all. I'm going to move it slightly on a little bit. We've got a comment. Where was it? So moving on to sort of instrumentation and monitoring. So there was a comment that was put up that for monitoring data, it's really important for engineers to understand that groundwater is not a static system and sufficient long-term data is needed, which needs to be specified early on in a project. And just to add to that, there's a question from Alan Williner in the back row. Do you want to ask it?
Particularly if we're doing deep boreholes on railways and nighttime sessions. And I wondered what your thoughts were about combining instruments in the same borehole. I've had trouble in the past having multiple levels of piezometers where the ceilings are very low. But can you advise on any risks combining interferometers with piezometers and extensions of piezometers when it does work, when it doesn't?
So just for those online, this is a question about combining instruments within a single borehole.
Really good question, and it comes back to a word that William used, quality, because essentially we are broadly here designers or implementation people to produce physical things, and we've been thinking about big railways, but some of you who work in investigation or that, the things you produce are boreholes which are later converted into data records for the geology, or in this case we're putting in monitoring instruments, inclinometers, open standpipe piezometers, or let's say vibrating wire pressure sensors. As the first thing is that you need to specify something that can be constructed at that location by the contractors available. So I've worked on mining projects and I absolutely specify not lower quality, more simplified monitoring wells if I'm working in West Africa than I'm working in West Bromwich, because I think that the supervision will be of lower quality and the contractors will be less experienced. Equally, you can take the view that if your conceptual model should be driving your design of your instrumentation. So if you're intending to have multiple level piezometers, let's say, that will come from conceptual model, and then you would say, can I make that a fully grouted multi-level sensor borehole? Which nowadays, once you get more than 2 level sensors, I'm absolutely want to go down that route because it's been demonstrated the last 20 years that fully grouted piezometer installations designed and installed by experienced contractors, give high quality results. Like you, I'm wary of multiple response zones in standpipe piezometers because you get leakage between them. You can do them on some locations with good contractors, but I've probably not specified multiple level piezometers for standpipe piezometers for about 5 years because I think now that the vibrating wire piezometer is going to take over. But the point comes back to quality. Was that phrase by John Ruskin? Quality, is never an accident. It's always a result of intent. And I think we should recognise that monitoring wells need to be designed just like a railway needs to be designed, a monitoring well needs to be designed, and it keeps coming back to, I'm afraid we keep saying this, to the conceptual model.
Right, I'm going to go for the final question before I close up the session tonight. Love this. Molly, 5th-ish row from the front. Early consultation has been a key theme throughout the presentation. How do you ensure early hydrogeological input on projects? I'm going to maybe go Mark for that one.
If I knew the answer to that, I'd be rich. I'd be retired. I wouldn't be here. It's for anyone that's worked in groundwater in sort of consultancy or professional practice. It's a bit of a challenge because it's really hard to get your voice heard, and it's hard enough for anyone who works in the ground engineering world to get their voice heard on a big project, let alone sort of a niche specialism as it's viewed within that sort of subset of areas. So it's a lot of it's about kind of early communication, early profile raising, early awareness raising with kind of technical peers and colleagues within the business, but also kind of as a discipline, we don't really have a great track record of making a big deal of our successes. And there's a quote that my wife shared with me, which I really like, which is an extrovert engineer is one that looks at your shoes when they're talking to you rather than their own. And I think it's something that we do suffer from. We don't like to make a fuss about the fact that we've saved all this money or we've avoided all these problems. And so clients don't see the value that we add. All they see is a line item on their bid that says we need these experts to give us some advice, and we don't know what they do. So why should we do that? And then when you sort of go down the levels to the individual disciplines that contribute to that, it gets harder and harder each time because you've already had the top line cut. So then you suffer even more as you get to the specialist bits, and then it just kind of perpetuates itself. So I think the biggest bit of advice about how to get hydrogeological and geotechnical considerations early in these projects is to kind of make a bigger deal of our successes, both within our own businesses and also with the public at large. Because when people start being aware of what we do, and I'm probably biased, I think that we do some really interesting stuff, but you see documentaries on Channel 5 and things about like major infrastructure, and isn't it fantastic, and all this great stuff, like where are our experts, where are our people on the TV and high vis saying, and this is how we've dealt with this really difficult problem, and isn't that exciting? And pay attention more, and also consider coming into the industry, because there's not enough people coming through to do this for the future. So I think that's it's a bit of self-promotion and actually kind of making people aware of what we do, I think would be helpful.
I come back to my point on communication. If we're not getting the early engagement or involvement we want, we need to try and get that. And we need to think about the language our clients or the decision makers use and so on. So they think in terms of risk. And I'm sure we all produce risk registers, and a risk register, I think, is one of the most unintelligible things you're ever going to produce in your life. You still clearly need to produce them, but the other ways of communicating risk. And on big projects, I think time costs a lot of money. And there is an argument that if you spend £50,000 on an investigation, that then lets you put in £100,000 of ground improvement or groundwater control, but that can, to a very high degree of certainty, avoid a major delay of a month on your project. That month's going to be worth a lot more than the £150,000 you're proposing to spend. And I'm not convinced the sort of people in this room who are, technically people, I'm not convinced we communicate that in that way that's enough. because we need to recognise that most of us aren't big decision makers or big budget holders, but we can have an influence on those decision makers and budget holders, and we need to figure out the best way of achieving that.
So I think, yeah, perhaps just to reinforce both those points, I think it is very much about understanding the language that needs to be used to try to communicate with people. And Fleur, in her lecture, which some of you were at, talked about the, let me try and get this right. Fleur talked about the time cost of money, but actually the money cost of time, which is what Martin has just alluded to, and the need to de-risk things is important. And the one thing that I think I might add is I think trusted relationships are really important. So that I've been aware of a couple of jobs recently where a scheme has been developed with a specialist subcontractor, not necessarily just for dewatering, but dewatering was one of them. The other one was something slightly different. It then, of course, has to go out to tender. The scheme goes to a different subcontractor who doesn't really understand the concept, and then it all goes a bit Pete Tom. So I think actually trying to establish a relationship of trust on both sides between the client and the specialist is also really important. And sometimes we get an opportunity to do that and we blow it. And that I think is unfortunate because it then makes it difficult the next time.
Can I just sort of add to that? Yeah. Sorry, the microphone just went for a quick journey. William and I are old enough where we recognise that the construction industry in the UK goes through cycles, and when we started out in the 80s, it was the construction industry was very disjointed, and there's a very strong distinction between permanent works and temporary works. So the permanent works designer would not touch temporary works, and the temporary works were very much an afterthought, I think. And then following things like the Egan Review and the Latham Review in the late 90s, design and build came in, and there was a much better integration between permanent works and temporary works, because obviously if you get them to match up, there's real cost savings about. There's real synergy, to use a word comparable to holistic. There's just a real synergy between them. But I get the feeling we've gone away from that now, and I get the feeling on HS2, for example, that the main designers design the permanent works and they do not design the temporary works. And I've seen examples where I don't think that's working. And that means then that specialist temporary works contractors, piling contractors, dewatering and so on, who have real knowledge, aren't involved early enough. So I wonder whether we're going to need to learn the lessons of, to be frank, the failures of success of some of the current projects, and have to go through another cycle. And everything's cyclical, but I think we're in quite a negative part of the cycle at the moment.
So if I may, I mean, at the risk of being slightly controversial, a different project, the Great Western Electrification, that just sort of, the budget, it just went massively over budget. You got to a situation whereby the money was going to run out to put up the infrastructure. Once they ordered bi-mode trains, it doesn't really matter where the electrification stops, because, you know, that die is cast. And in my opinion, that was, I think, certain elements of the civil engineering industry who just thought, well, hey, we're onto a winner here. They decided that they would over-design all of the foundations for the electrification mast. They decided that they would produce an individual bespoke design at some considerable cost for all of that. And they just thought the client had got a bottomless pocket and would pay. Well, breaking news, the client doesn't have a bottomless pocket. The client got fed up and said, actually, we've had enough of this, we're going to stop it. So electrification was paused for quite a time. It's just about sort of restarting again. And, you know, in a sense, with HS2, for whatever the reasons, the cost balloons, and the political will sort of evaporates, and then actually it's an opportunity that's blown. So I do think it is really important that this trust, so going back to Martin's point, you know, I think we have become kind of quite mechanistic, quite compartmentalizing of things, and quite, you know, actually, I don't care about minimizing the system risk. I care about minimizing my risk. And even if that makes the system risk balloon, I don't care. So we've sort of created businesses where we have got massive friction at interfaces, multiple parties involved. And sadly, all of that kind of is viewed in the post-Thatcher economic model as economic activity. It isn't. So, you know, Euston Station has been designed 3 times. And what have we got to show for it? A hole in the ground. And yet it's all economic activity because people have put in the work and they've done the consultancy, etc., etc. So I think I'd agree with Martin that we're in a bit of a low point in the cycle, but I think these things come around again. But building trust, I think, is important.
Excellent. Thank you very much, guys. And just a round of applause again for our speakers. Thank you. So in BGA ECG sustainability style, we will be sending a houseplant gift card to your door to buy a sustainable plant as a note of thanks for each of you for this evening. Just again, thank you to our series sponsors for helping us put these talks on, all on the screen. Got the future sessions lined up, so stay tuned for announcements on those. Just a few other promo bits before I let you go. There is a Young Geotechnical Engineers Symposium in Cambridge in July. There's more information online for registration. They're accepting talks, and I understand there's a poster competition. So if you're interested in presenting at that, go check it out. There is also another MOGE lecture, also up in the north, in Sheffield, on the 14th of May, hosted by the Yorkshire Geotechnical Group. It will be an in-depth look at a different chapter, economic design of foundations. So look out for that, refreshments available as well. And final one from me, for those of you who are early careers in the room, there is a BGA fund, and this is a lovely pot of money that is issued out twice a year to any early careers individuals who may need assistance with attending a conference, undertaking some field studies for work or study, any equipment that you might need to assist with your work. I really strongly advise anyone to submit for this. The deadline is the 31st of May, so you've still got a month, and applications are reviewed shortly thereafter. There have been some really great testimonials of things that the individuals have been able to do with this fund. It's up to £1,000 per case. So head to the BGA website for more details as well on that. So with that, that's the formal close of the event. So thank you all in person and online for joining. And yes, thank you.